University student branch. It's an absolute honor to welcome you all in today's webinar entitled Transformerless Photovoltaic Grid Interface for Distributed Generation. We are euphoric to have such a distinguished audience with us as we dive into the webinar. So this is the webinar which is jointly organized by the IEEE Primary University Student Branch and IEEE BSMRTSU Student Branch. So before we begin, I would like to extend my heartfelt gratitude to our esteemed guests who have joined us today. We are privileged to have Dr. MD Mustaq Ahmed, the faculty member of the Department of Tripoli Prime University, and Dr. ATM Saiful Islam, the counselor of the IEEE BSMRSCU student branch, and also the chairman of Tripoli department. And it's my great honor to introduce our distinguished speaker for today's webinar, Dr. NILyoutube, Associate Professor in the Department of Tripoli at Agnel Charities FRC Rodriguez Institute of Technology, Vasi. Dr. Rajiv holds a PhD from IIT Bombay and has authored over 40 research articles in various journals and conferences. She has also successfully completed several funded research projects. Your presence adds immense value to this event, and we are grateful for your support and encouragement. Without any further delay, let's dive into the session we are waiting for. Please join me in welcoming our guest speaker, Dr. Rajiv. The stage is yours. Please begin.
Thank you. Before starting, once again, thank you for inviting me for this seminar. Before starting, I would like to know what is the background of this students. They are from which year?
Yes, they are all from the electrical and electronics engineering department.
And which year? All years or?
All years,
Second,
first to last.
Okay, so they have covered a course on power electronics or something like that?
Several of them have already completed this course.
Yeah, okay, fine. I will start. I will close my video and I will share my screen.
Yes, please.
Is it audible? Seen? My.
Yes, madam.
Okay. So, as we mentioned, the topic is transformerless photovoltaic grid interface for distributed generation. So, this will be my outline of the presentation. I will briefly mention about distributed generation and photovoltaic systems, then power conversion in grid-tied systems, transformerless grid interface, and control aspects and grid support and the research trends. So distributed generation means generation of electricity near to the point of consumption, which means that if I'm installing a rooftop solar PV in my house, that is also a distributed generation because I'm generating and I'm using at the point of generation itself. So advantages, it can be distributed generation can be by renewable sources as well as non-renewable sources. But advantages if you use renewable sources are less environmental impact because you are not depending on fossil fuels when you do distributed generation by renewable sources. Then no transmission and distribution losses as you are using or as you are not transmitting or distributing, you are consuming it at the point of generation itself. I will take one pointer. So then reduce dependency on conventional sources which will help in preserving our fossil fuels, as we know that fossil fuels are getting depleted. Then grid support, we can give grid support also, that I have a separate slide. I hope the PPT is moving. You're able to see the next PPT, right?
Yes,
Yes,
madam.
yes, ma'am.
Okay, thank you. Okay, so renewable sources for distributed generation. There are many renewable sources for which comes under distributed generation. Today, we will be talking about solar photovoltaic system. Now, solar photovoltaic system has become very popular in distributed generation because there is a steady decline in the cost of PV panels. Around, I think 20 years back, when I bought a PV panel for my research work, I paid around 250 rupees per wattage for that panel. So I have bought around 75 watt peak panel and I paid around 18,000 rupees. But now if you buy a PV panel, cost is around 20 rupees or less than that per watts. So steady decline is there in the cost of PV panels. Then improvement in the conversion efficiency, maybe because of the manufacturing techniques or the material with what they are using for the solar panel, the efficiency of that improved. Then there is a huge potential in a tropical country like India because the sun shines for more number of hours. And operation life of PV is higher, around 20-25 years. After 15 years or so, the conversion efficiency will reduce little bit. Nowadays, we get panels with around 20% conversion efficiency. And after 25 years, also you can use the panel. That is what those who are using the panels are telling. But the efficiency will be lesser. But still, it will generate power. Less pollution and maintenance as compared to fossil fuels, the pollution is less and it is comparatively maintenance free. Occasionally you need cleaning of PV panels so that the dust and all will not reduce the conversion efficiency. And you have scalability, which means that if you want to increase the power level, you can always add PV panels to it. So that is why photovoltaic system is more popular in distributed generation. Coming to types of solar photovoltaic systems, there are on-grid systems, grid tied with battery backup, and off-grid systems. Now we will be speaking more about grid-tied systems. Now, grid tied with battery backup we need for two reasons. One reason is to provide the power. Suppose I'm generating at my house. If there is a grid outage, I can use the battery power for my house. Another thing is to match the demand and supply. Sometimes the peak demand or peak requirement of the grid will be very high. So that time, if you use the battery backup, the grid need not or the fossil fuels can be preserved. So that is why grid tied with battery backup is used. Then we have off-grid systems, which are also known as standalone systems. So can someone tell me some examples of standalone systems? Standalone means which is not connected to grid. You are generating power and using it. You are not connecting or giving it to grid. Can you tell me some examples of standalone systems? Anyone?
Ma'am, when we are using a photovoltaic solar cell in my own house and we are not connected in grid,
Yeah.
ma'am.
Yeah,
Yes, ma'am.
okay. Yeah. Household system is a standalone system if you are not giving it to power to the grid. You are using only for your house. That's correct. Or people use it for pumping water in farms and all. Whenever sunlight is there, they pump the water for the farms. So that is also a standalone system. There are many examples. Street lights are there. Then EV charging stations are there. Many examples are there for standalone system. So now we will concentrate on grid-tied system. So for grid-tied system, there are some standards for interconnecting distributed resources to the grid. There are IEEE 1547, then International Electrotechnical Commission standards are there, European standards are there, German standards are there. All this are related to interconnecting distributed resources to the grid. Now, this VDE 012611 is specifically for this grid interface. That includes transformerless grid interface also. Now, you know that there is PV that generates DC and grid is AC. So we need some conversion, power electronic conversion in between. The DC should be converted to AC. There are some demands defined by the grid, by the PV modules, and by the operator. Demands defined by the grid include power quality, which includes all that voltage sags, voltage swells, all that time you should maintain the power quality. And then grounding issues. You should also take care of the safety part of it. For single phase grid, the neutral should be grounded as per standards. Then reactive power support. This will help again in peak demand. When the voltage sag occurs, if you provide reactive power support, you can bring it back. The voltage which was reduced, you can bring it back. So you can provide reactive power support. Then detection of islanding operation. You know what is islanding operation? Anyone? What do you mean by islanding operation? Any idea?
Ma'am, when we will not connect our consuming part to the grid, and it will be separate, completely separate. That's the system said the island.
Actually, I know it's something related, but suppose the grid fails, but your inverter will still be supplying to some section of the grid. So that is what you mean to say by islanding operation. Okay, that needs to be detected because the grid is, suppose the grid fails and that section, the grid power is not there. Some operator or somebody who is working on that inverter side of the PV will get a shock, or somebody who is coming for grid maintenance, not at the inverter side of PV, somebody who is coming for grid maintenance will get a shock if the inverter is still supplying power to the grid. So that is what islanding operation means. Okay, so this inverter will still be connected to the grid. Grid is not there for some maintenance or some outage. Grid power is not there. But inverter, we are generating from PV through inverter. Inverter means DC to AC converter, and we are giving power to the grid. So that will still be there. That is known as islanding operation. That needs to be detected. Otherwise, the person who is coming for maintenance, it will be dangerous for them. So that is islanding operation. So that is also a requirement by the standards. Then demands defined for the PV modules. We know that sunlight is abundant, but we get PV output is very less because the conversion efficiency is around 20% or so. So 80% we are not able to convert 80% of the sunlight. So to improve the efficiency, we use maximum power point tracking. I have a slide on that. And also there should be less ripple at the input terminals. If the ripple is more, that will also affect the maximum power point tracking efficiency. Then of course, demands defined by the operator like us, cost effectiveness. We don't want to pay more. High efficiency at a wide range of input voltage, because we know that solar panel operates at a wide range because it is affected by intensity of light and also by temperature. So your efficiency should be there for that range of input voltage. Then high reliability. Okay, that power, whatever we are getting, it should be reliable. So these are the requirements of the grid-tied PV systems. Now, power conversion in grid-tied photovoltaic systems. There are three types of power conversion. One is two-stage conversion. Another one is single stage with transformer and single stage without transformer. I am talking about single phase systems. I am not talking about three-phase systems in my seminar. So there are two-stage system, which means that there are two stages. These two are single stage systems, which means that there is only one power conversion stage. And one is with transformer and other one is without a transformer. So one by one we'll see. This is a two-stage conversion where you can see that there is a DC to AC converter. Sorry, there is a mistake in this. One second. Yeah. So this is two-stage conversion with transformer. There from PV, you have a DC to DC converter, and this will be an isolated DC to DC converter, which means that there will be a transformer in this. There are different types of DC to DC converters. You have studied any DC to DC converter with transformer? Like flyback, forward, full bridge, push-pull. There are so many converters with high frequency transfer. Yeah. So this is an isolated converter where you use a high frequency transformer in this. Okay. And then the output of that will be given to an inverter. And inverter output is not pure sinusoidal. So you use a filter to filter out the high frequency components. And then it is given to the grid. There are two power conversion stages. So since there are two power conversion stages, the efficiency will be lesser in this. But from the control point of view, it is better because you can control independently DC to DC converter for the DC side and DC to AC converter for the AC side. Coming to single stage transformer, single stage power conversion with transformer, you have only one inverter there. You have one inverter and then the inverter output is filtered to make it a better sinusoidal output waveform. And after that, you will step up the voltage to feed the grid. Now, because transformer is there, you can have less PV voltage or less rated PV panels. Now, if if the PV panels are connected in series and if a partial shading occurs, okay, the efficiency will get affected and it is dangerous for the PV panels also. So it is always better to connect PV panels in parallel. So here, if you use a transformer, series connection of panels can be reduced. In this case, that issue will not come because you are using a transformer. Here also, you are using a transformer. So that issue will not come. Means you need not connect more number of series connected PV panels or PV modules. Coming to single stage transformerless conversion. Here you can see that there is no transformer at all. So there is a PV panel, there is a DC to AC, that is inverter, and then filter. Filter is common for all because the inverter output is not a pure AC. So you need a filter in all the three cases. So filter is used and there is one inverter. There is only one power conversion stage similar to this one. So the efficiency is better than two stage. And the number of components are also lesser. So the reliability is also more. But what is the problem with this? One problem is you cannot step up the voltage at the grid side. So it will be better if the inverter is having a boost capability. Boost capability in the sense, step up capability. And another advantage is because the transformer is eliminated, it will have better efficiency, lesser weight, size, and cost. So these are the advantages of transformerless power conversion. But what is the cost we are paying for? Nothing comes for free. So the main issues of transformerless PV grid systems are, one is ground leakage current. According to this German standard, leakage current must be lesser than 300 milliamperes. And DC injection into the grid. Now, DC injection comes if the inverter output is not symmetrical. Means DC injection means if the average value of that output voltage or output current is 0, then there is no DC injection. If the output of the inverter is having a DC value, then the DC will be injected into the grid. That means average value is finite. Then DC will be injected into the grid. Now, this creates many problems like it will saturate the distribution transformers and it will increase the losses in the system. So, there is that standard says, IEEE 1547 says that DC injection should be less than 0.5% of the rated output current. Now, IEC says that it should be less than 1% of the rated output current. But there is limitation according to the standard. So, right now we are talking about, we'll be concentrating on the ground leakage current. So now we will see why this ground leakage current exists in a transformerless inverter. So this is a PV panel, cross-sectional view of a PV panel. There are PV cells, there is glass, there is a substrate, and there's a metallic frame. And the metallic frame is earth for safety reasons. So that when an operator touches the PV panel, he should not get a shock. So the PV panel metallic frame is earth. So you have two conducting surfaces and in between some insulating area. So it will act like a parallel plate capacitor. So that is what we call it as parasitic capacitance. There is no physical capacitor, but it will act as a capacitor. So this parasitic capacitance depends on type of solar cell. Then there are different types of solar cells like polycrystalline, monocrystalline, thin film. All types are there. So depending upon the thickness of all this, the type of solar cell, this capacitance will vary. Then depending upon the surface area of the solar cell, again this capacitance will vary. You must have studied that the parallel plate capacitor is epsilon A by D. A is the area, D is the distance, and epsilon is the permittivity. So surface area, if it changes, capacitance value will change. Then environmental conditions. Can someone tell me with how this capacitance can change with environmental conditions?
Ma'am, dielectric media epsilon is the
Yes, very good. So permittivity will change. Permittivity will change. So epsilon A by D, if permittivity changes, then also capacitance will change. Then dust. Similarly, dust also. The distance between that one will get affected by the dust. So that also will change the capacitance value. Okay. Then again, distance between PV cells and the metallic frame. All this will affect the parasitic capacitance. And these values are 50 nanofarad per kW to 150 nanofarad per kW for monocrystalline or polycrystalline panels. And since thin film area is lesser, it is higher. It is around 1 microfarad for thin film panels. Now, how this? So now we know what is this capacitance, parasitic capacitance, and that exists in a when you have a PV grid system. For I also said that the PV panel metallic frame is grounded for safety reasons, and the grid neutral, single phase grid neutral is also earth for safety reasons. As per standards, that is a requirement. So there is a closed path like this for the current to flow. Okay. And there are two currents in this, like op-amp circuits and all you must have studied, common mode current and differential current. Similarly, there is common mode current, common mode voltage, and differential current and differential mode voltage here. Differential current means it is a current which flows like this and goes back. IA minus IB you can see. Common mode current is IA plus IB. So this common mode current will flow through this capacitance, through the system. Okay. And why this current is happening? Common mode voltage definition is VAN plus VBN by 2. Here we are taking A and B as the terminals of this inverter. So voltage of A with respect to a common point plus voltage of B with respect to a common point divided by 2. This is the definition of common mode voltage. So if this voltage varies, then the capacitor voltage will vary. If the capacitor voltage varies, there will be a current, C dV by dt. So there will be a current through the capacitor. Now, how this voltage varies? Common mode voltage varies. Now, this is the inverter circuit. This you must have studied. This is a single phase bridge inverter. And we use sinusoidal PWM techniques, mainly bipolar PWM and unipolar PWM techniques for this inverter as a modulation technique. So when you use bipolar PWM, there is no issue. There is the common mode voltage will be constant. So I'm not talking about that right now. But when you use unipolar PWM is this one. You will have a triangular wave. PWM means you will have a triangle, which is called as a carrier wave, triangular wave, and then a sinusoidal signal. For unipolar, the sinusoidal signal, there are two sinusoidal signals which are apart by 180 degree. In bipolar, there is only one sine wave and a carrier wave. So in this case, this bipolar SPWM, why it is called bipolar? Because the output you will have in each half cycle, both polarity output. Whereas in this, you will have only single polarity in positive half cycle, and for each switches I'm telling S1 and S2 and S3 and S4. And you will have negative polarity only for negative half. That is why it is known as unipolar. So when you talk about unipolar PWM, what we do basically, first we will switch on S1 and S2. So this is an inductive load. So as usual, the current will flow from VDC, S1, S2 and back to the supply. Then S1 and S3 will be on. S1 is already on. So S1, we will keep it on. Then the current, if it is an inductive load, the current will circulate or it will discharge through D3. D3 will be forward biased at that time, because when the inductor discharges, the polarity is changing. Di by dt is negative, rate of change of current is negative. So the voltage polarity will change. So D3 will be forward biased. So the current will flow through D3, through S1 and back to supply. So that time, the voltage VA, this and this are at same potential. So VAB, VAN plus VAN by 2 will be 0. Whereas when S1 and S2 are on, when S1 is on, A will be at the positive point, and here, if the negative you are taking as the common point, VAN will be VDC and VBN will be 0. So VAN plus VBN by 2 will be VDC. Is that clear what I am telling?
Yes.
S1 and S2 I am turning on. So when S1 I am turning on, this will act as a short, imagining that the switch is ideal. So this point is connected to this positive. So, and if I take this as a common point, I will get VAN as VDC. And this I am shorting. So VBN will be 0. So VAN plus VBN by 2 will be VDC or VDC by 2. But when you am turning on S1 and D3, the voltage is 0. So there is a variation of common mode voltage. That means across the capacitor, the voltage is varying. So there is a current. And this leakage current will not affect if the transformer is there, because this transformer will not transfer DC current. Okay, so in case of if transformer is there, this is not affecting us. And if transformer is not there, then this also will be injected into the grid. So this VCM means common mode voltage. Common mode voltage variation produces ground leakage current. And again, the magnitude of that depends on the structure of inverter, the modulation strategy, as I said, unipolar, bipolar, and also the value of CPV. Value of CPV, we have already seen how it gets affected. And this leakage current will increase the losses As it is a high frequency current, it will increase the distortion. It will interfere with the radio frequency signals. So overall, this leakage current needs to be eliminated. So as I mentioned before, according to standards, the leakage current should be less than 300 milliampere. Whenever transformerless inverters are installed, there are residual current monitoring system. This system will measure this leakage current or sense this leakage current. And if it is more than 300 milliampere, this will disconnect the inverter system. So in order to eliminate this, or in order to make the leakage current below 300 milliamperes, we need modification in the inverter structure or in the modulation technique. So I will show you how they are modifying the inverter structure. So these are some of there are a lot of transformerless inverter structures or topologies. N number of topological structures are there. I am showing some commonly used transformerless single phase inverters. H5 inverter, this SMA inverters, SMA company is using that in inverters. Herrick topology is also used. Neutral point clamped is also used in industry. So this you can see, this is a full bridge converter. Only they are adding one S5 switch here. This capacitor that we are adding for all to reduce the ripple that you leave. So S5, that one additional switch is added in H5 topology. And in this case, you can see that there is a switch, additional 2 switches at the AC side. And in neutral point clamp, it is clamped from there is a split capacitor and there is a clamping here. So similarly, this flying inductor, 4 switch converter, 5 switch, this 5 switch converter is derived by me and my guide in my laboratory only. So that I will show you in little bit in detail. There are papers also, my papers are there in IEEE related to this. So I will just tell you how during this this H5 topology, how it is taking care of the leakage current. So during positive half of the grid voltage, S5, S1, S2 are turned on. That means S5 is on, S1 is on, S2 is on. Okay, so use normal way of single phase bridge inverter, like that it will work. Which means from PV, the current will flow through S5, then through S1, then through this. This is filter, okay, LA and LB. And then through this and through S2 and back to the PV. Now, when the inductor is discharging, during freewheeling stage, diode of S3 and S1. Okay, so this will freewheel like this through the diode and through this switch and back to the inductor. During that time, S5 is kept open. So we call it as decoupling of the PV panel and the grid. Okay, so this will reduce, if you are keeping it open, this will reduce the variation of the common mode voltage. You are decoupling the AC side and DC side. Similarly, during negative half cycle. This happens in H5 inverter. Similar thing happens in Herrick inverter, but on the DC side. It will be decoupled from the DC side during freewheeling operation. So this makes the common mode voltage constant. So that is how the leakage current, that means the capacitor voltage remains constant. So again, C dV by dt, if the rate of change of voltage is constant, the current is 0. So that is how they are eliminating the ground leakage current for transformerless grid interface. So from this, what we can understand is by modifying the single phase bridge topology in such a way to make the common mode voltage constant, we can eliminate the leakage current. Another method is you can short the grid and the PV directly so that the capacitor will not come into picture. That I will show you. So before going to the control, I will just tell you what is the grid connection principle. So this is the equivalent circuit of the PV inverter connected to the grid, not necessarily PV inverter, any inverter for that matter. So in our case, we will consider this as a PV inverter. Now, we cannot connect 2 different voltage sources in parallel. We need some energy storage in between. So here I am showing an inductor. So there is an inverter, inductor is there, and a grid voltage. So phasor addition, inverter voltage will be phasor addition of VL inductor voltage and grid voltage. Now suppose you want to feed active power to the grid. So that means the grid current and grid voltage are in phase. So that is what I am drawing here. Grid voltage I will draw as reference and grid current is in phase. So then I will draw VL. VL, how should I draw VL? Can you tell me? I have the I grid here, which is the current through the inductor. So can anyone tell me how will I draw V grid here? VL, inductor voltage. Suppose I have to draw from here. How will I draw? Upwards or downwards?
Inductor, it will be upward.
Yeah, it will be upwards. It will be upwards because the grid current which is passing through the inductor will be lagging the inductor voltage. So that is how the same thing I am drawing it here and finding the resultant. So this is my inverter voltage. Okay. So what do you understand from this? For active power transfer, there should be some phase difference between the grid voltage and the inverter voltage. So while in the control algorithm, we should make in such a way that, or the control strategy should be such a way that there is a small phase angle difference between the inverter voltage and grid voltage for active power transfer when you connect PV to the grid. Similarly, if you want to reactive power, if you want to transfer, reactive power, then same way grid voltage I will draw. Reactive power means the grid current will be 90-degree lagging the grid voltage. So again, inductor voltage I will draw like this, leading the grid current. So this I am taking from the tip of phasor V grid. So addition of these two, I will get V inverter. So what do you understand from this? For reactive power transfer, what should I do? I am generating the inverter voltage. Grid voltage is constant. Let us say single phase 230 volt RMS. And I am generating the inverter voltage or 325 peak grid voltage. So what should be my inverter voltage? Can anyone tell me?
Ma'am, grid voltage added with the VL, my load inductance drop.
Agreed. So what should be, when I am feeding it to the grid, what should be my inverter voltage? More than grid voltage or less than grid voltage, magnitude wise?
Ma'am, inverter voltage will be more than grid voltage.
Correct. So for reactive power transfer, the magnitude of inverter voltage which I am generating should be more than the grid voltage. There is no phase difference, you can see here. But for active power transfer, there should be some phase difference between the inverter and the grid voltage. Okay, so that is the grid connection principle. Now coming to the control block diagram. So this performance of this depends mainly on the control strategy. So this is the block diagram. This is the inverter, transformerless inverter topology. Again, filter, all inverter, as I said, will have a filter because the output is not sinusoidal. You have MPPT control, reference current calculator and grid synchronization. That's what I've written here. Control includes DC side control, grid synchronization, reference current tracking and reactive power support. So first is DC side control. So DC side control means, as I said before, the tracking power conversion efficiency of PV panel is less. So through maximum power point tracking, we can improve the conversion efficiency. This characteristics you must have seen. So we should always make our PV panel work at these points so that the output we are getting the maximum power. This is the block diagram for that. We will sense the PV current, PV voltage, and there is the MPPT algorithm. There are different types of algorithms. Have you heard about this maximum power point tracking algorithms? Can you name any one or two?
age tracking, rainflow, that's kinds of.
What is that? What is that? No, I couldn't hear you properly.
I just forgot. I just forget. There was 3 method I learned 2 days ago. Just I don't remember now.
Okay, no problem. See, there are perturb and observe method, which is called as P and O method. Then there is incremental conductance method. There are different methods: particle swarm optimization, model predictive control. There are many sliding mode. There are many control methods for this. Okay, not control methods, MPPT algorithms for this. So we will use the most simplest is the P and O method, perturb and observe method. So what we will do, we will give a small perturbation in the voltage and we will write a program to check the power. I'm not going to detail of that. That is a separate topic as it is. So, but here we will track the maximum power using this MPPT algorithms. So from there, we will get a maximum voltage. So that we will compare with the VPV, and the error we will pass through a PI controller. So our aim is to make this error 0. That means this VPV and VMPP will be same. So this IG peak will be the peak current that needs to be injected to the grid. So that is one DC, that one control, one side control I should say, that is DC side control. Next is grid synchronization. When you generate from an inverter, your voltage and frequency should match with the grid voltage. Okay, depending upon active reactive power, there will be small difference in phase angle or magnitude, but otherwise it should match. If you're transferring active power, your magnitude should match, your frequency should match. Otherwise, there will be circulating currents. If there is a difference, there will be circulating currents, and due to grid will not get affected by that. What will get affected is our inverter or the devices and capacitors, all that in the inverter. So we need to synchronize with the grid. That means when you are generating the voltage, we should make sure that it is similar to the voltage is same as grid voltage and frequency is same as grid frequency. There are many methods again for that. The most commonly used method is phased locked loop method, PLL methods. So this is the general PLL structure for single phase systems. You have studied this PLL structure anywhere? Maybe in op-amps. Anywhere you have studied analog electronics or in power electronics?
Ma'am, we are familiarized with the cycle
PLL.
converters.
Okay, fine. So this phase loop methods are, these methods are used for grid synchronization. Okay. But in single phase systems, there is a challenge because you need 90-degree phase shifted signals here. So how to generate that 90-degree phase shifted signal is a challenge in single phase. In 3-phase, there is no issue like that. There are already phase shift, there are phase shifted signals by 120 degree. But here you need to generate it. So based on that, the PLL names are there. There are many methods are there, T/4. I am not going to detail. But so finally, what you get from here is sine theta. Okay, and that theta will depend upon the grid frequency. So next is, so first one was DC side tracking. The next one was grid synchronization. The third one is the reference current tracking. So for reference current tracking, what we do is, this is the IG peak from maximum power point tracking algorithm, which we have seen. Then you have the sine theta from PLL for grid synchronization. You are multiplying that. So we will get IG sine theta. So this will be your peak current. And then you will subtract it from IG. And that this output will be your IG reference. And the this error is passed through your PR controller, and the output will be your modulation index. Again, you will have a sinusoidal PWM, and then pulses are given to the inverter. This is by using proportional resonant controller. Proportional resonant controller acts for sinusoidal signals. Okay, this 1 second. This reference is here. Okay, so the error is passed through a PR controller to make the error 0. And then you have sinusoidal PWM technique and the pulses to the inverter. Now, suppose you want to use a PI controller, proportional integral controller, which is very commonly used. Then you have to go for the synchronous frame control. Now, why you have to go for the synchronous frame control? Because in PI controller, the error will be 0 only if it is DC signals. This will not work fine with sinusoidal signals. Whereas proportional resonant controller will work fine with or work well with sinusoidal signals. This IG and IG reference both are sinusoidal signals. So PR controller, there is no problem. I will tell you why also. But in case of PI controller, you need DC signals. So that is what all this is done. This synchronous frame transformation is done to make it DC. So the final comparison, when you do ID reference and ID and IQ reference and IQ, these are DC signals. Now, why is it so? You can see here, the PI controller, the transfer function of PI controller is Kp plus Ki by S. Now, if S is the frequency, if I am putting S as 0, I will get gain as infinity. If I am putting S as 0, Ki by S will be infinity. So this gain will be, or transfer function will be infinity. Transfer function means gain. Gain will be infinity. So you have studied in control system that the steady state error is inversely proportional to gain. So if the gain is infinity, steady state error will be 0. So ideally speaking, what we want is the steady state error should be 0. So in PI controller, we can get that for DC. Frequency I am putting 0 for DC. But if I put a value for this, suppose I have a 50 Hertz signal, AC signal. I am putting S as 50, J omega. So J 2 pi into 50. If I am putting that, the gain will not be very high. So the steady state error will not be 0 if you are tracking sinusoidal reference current using PI controller. That is why directly PI controller is not used if you have to track sinusoidal currents. But you can use a proportional resonant controller. The transfer function or gain of this PR controller is this way. So here if I put S as omega, which is grid frequency, then the denominator will be 0. Both are same frequency, so denominator will be 0. So gain will be infinity. So again the steady state error will be 0. So this is the body plot of the PR controller. You can see that at 50 Hertz, the gain is very high. So that is why to track sinusoidal signals, you prefer PR controller. Now this is a transformerless grid interface with control. This we have seen earlier. There is a PV panel, then inverter, transformerless inverter, filter and the grid. And you have MPPT, you sense PV current and PV voltage. And then you are passing through a control. And you have sensed grid current and grid voltage. So this control, what all it will, what all aspects are there in this control? Can anyone tell me? What all aspects will be there in this control? I had mentioned 4 aspects and 1 is taken care in MPPT. Which are the remaining 3? Can anyone tell me?
Ma'am, we didn't understand your question. Can you repeat?
Yes, I will repeat. See, I said that when you talk about the control aspect of a PV inverter, there are 4 aspects of it. One is DC side control. Okay. DC side control means it takes care of this MPPT and all.
Yes, ma'am. And second one is grid synchronization.
Yes. Second one is grid synchronization. And third one?
Reference current tracking.
Yes, very good, very good. Reference current tracking. So that's what I'll show you the slide again, which I mentioned. Very good. See, this is what I asked. I spoke about DC side control, grid synchronization, reference current tracking, and reactive power support. Okay. So this MPPT DC side control here I am showing separately. So this control will take care of all the other remaining 3. That's what I said. One is AC side control, another one is reference current tracking and reactive power support. all that this will take care of. I have a small quiz also before the last slide. Okay, now I'll show you how a new inverter topology can be derived. New means how a new transformerless inverter topology can be derived, or how I have done it. So that if you all want to do or derive a new topology or a new structure, you all can do it. So, so basically speaking, we need some boost also in transformerless inverter, as I said before. Means a step-up operation also we need. Otherwise, you need to use more series connected PV panels. So it is better to have a step-up capability in the inverter itself. Okay, so I have chosen a Chuk converter. There is inverting Chuk converter and non-inverting Chuk converter. So I have combined these two. You can see that in the input side, there is a DC source, there is an inductor, and there is a switch. Output side, there is load. This we will replace by grid, that I'll show you later. Right now, I am showing it as an resistive load. And there is a capacitor. Okay, this is a filter. And inductor, output side inductor. So this side is similar to the buck converter, and this side is similar to boost converter. And in between, you are using a capacitor and a diode. So that is what you call it as a Chuk converter. This is an inverting Chuk converter because the output polarity, the current will flow like this. Sorry, current will flow like this. So the polarity of the output is different from the polarity of the input. This is a non-inverting Chuk converter where the current will flow in this way. So these two I have combined. Now how I have combined, this remains the same. L1, S1 remains the same. This S2 I have added. Okay, this diode I have made it as a switch. Then this diode, there is a diode here, that also I have made it as a switch with an anti-parallel diode. All MOSFETs comes with a power MOSFETs comes with an anti-parallel diode. Then here, this is added. One S5 switch is added. So this part remains the same. Input source L1 and S1 remains the same. L2, C2 and this part remains the same. Only this capacitor also remains the same. Only one diode, two diodes I have converted to a switch with an anti-parallel diode and one additional switch. This is what? This is a transformerless inverter topology. There are 5 switches. Even H5 was having 5 switches. Okay. So this is the switching sequence. S1 will be throughout, it will be on. And other switches, depending upon the operation, it will be on or off. And S4 and S2 switches are operated at grid frequency. This will reduce the switching losses, though we have 5 switches. I'm not going to detail of that. I'm just giving you a hint that how you can convert an existing converter to a transformerless inverter. These two are DC to DC converters. I'm combining so that I get both positive and negative half cycles at the output side. So this I have experimental simulation also I have done to validate the design and the output. And experimentally also we have injected power to the grid using this topology. So this is the MPPT we have done. We have used a PV emulator for this. We have done, this is what it shows, that it operates at maximum power. Then this is the negligible leakage current. Leakage current we have measured using an RC circuit. This is the leakage current, which is almost negligible. Here you can see that this grid neutral is shorted to the capacitor, PV neutral. So the capacitor voltage is always 0. So since there is no variation of this capacitor voltage, leakage current will be 0. Negligible leakage current. This is how I generated switching pulses. I have used DSP TMS 320F28834, Texas Instruments DSP processor. Then this is for 200 watt power injection. These are the waveforms of the inductor, input inductor. This is the output voltage and the capacitor voltage, that intermediate capacitor voltage. Grid voltage and injected grid current. We got a THD of around 4.54%. We are measured using power analyzer. And then this is the dynamic response. If I change the reference, it is changing. This shows that if that PV panel reference is changed, the output will change. This is a 200 watt power level inverter. So we can use it as a micro inverter. Micro inverter means which is fitted at the behind the PV panel itself. So there are different types of inverters. I'll just show you that. There are central inverters, string inverters, and micro inverters in the order of power level. Central inverter, this classification is based on the arrangement of the PV arrays or PV panels. Central inverter is used for very high power level. Okay, but then there are drawbacks also. Long cables are required to connect this PV array to the inverter. Then there is only one inverter, and on that inverter we will do MPPT. So the MPPT efficiency will not be that good because all PV arrays will be at different locations. No? So the efficiency will not be that good. And string inverter, efficiency wise it will be better, but still a string of PV arrays are connected to one inverter, another string to another inverter, like that it is. Here, each PV array is having or is fitted with this inverter. Now, the drawback of this is you cannot have it for very high power level because the size and weight of this will increase. So this is what that photo I have shown. This is a micro inverter which is fitted below the PV panel. Now, the advantage of this is MPPT efficiency will be higher because each panel is having an inverter fitted to it, and where we do MPPT. So the efficiency of maximum power point tracking will be higher, or the conversion efficiency will be higher. So for residential applications and all, micro inverters are preferable. See that these are the standards. You can see harmonic currents. Individual limits are there for harmonic currents. Total harmonic, THD means total harmonic distortion. That should be less than 5% when you generate from the renewable sources and feed it to the grid. The THD should be less than 5%. And as I said before, DC current injection should be less than 1% and less than 0.5% for some other standard. That depends on the standards. Now, next is what all services this PV inverter can provide. And ancillary services means the services provided by the PV inverter to ensure the stability and power quality of the grid. Now, we know that there is high penetration of this PV or all renewable sources. So this can cause voltage variations in the grid. So there are voltage regulating equipments. You must have studied that on-load tap changers, off-load tap changers, capacitor banks, etc. But these are not that fast. And harmonics generated due to switching of capacitor banks can damage the PV inverters. Then connecting FAC devices. That also is a solution, but additional cost you have to incur. Instead of that, if the PV inverter itself can improve the stability and power quality of the grid, that is a good option. So that is what I mean by ancillary services. I'm not going to detail of that, but I'll just tell you what all ancillary services a PV inverter can provide. Reactive power support, as I said before, you can, instead of active power, you can feed reactive power to the grid if there is a voltage sag or anything. Okay, voltage regulation and provide reactive power for machines so that grid is free from these reactive power support. Then harmonic compensation. You can provide, PV inverter can compensate the harmonic currents. Again, the grid will be free from supplying these harmonic currents. Then low voltage ride-through capability. For small voltage sags and all, the inverter can still remain connected to the grid and provide reactive power support. That is what you mean by low voltage ride-through capability. Inverter will remain connected and it can provide reactive power support. It can also regulate frequency by active power control. So coming to the solar rooftop system, what all you require for a solar rooftop system, you need solar PV modules, inverter, module mounting structure, bidirectional meters, because we have net metering, balance of the system. which includes all the cables, switchboards, all protections, etc. So this is the block diagram of a residential application, solar rooftop system. PV array, DC disconnect, it is seen all this here. This is an inverter, red color, and these are the AC disconnect, DC disconnect and all. Array DC disconnect, inverter, AC breaker, residential loads we are giving. And through a bidirectional meter, we are also giving it to the grid. This is an on-grid example of an on-grid 2.2 kilowatt solar rooftop installation. This is done at my house. Rooftop area utilized is 200 square feet, shadow-free area. And PV module, what we have used is 545 peak, 24 volt vary. Number of PV panels, there were 4 for 2.2 kilowatt. That is 2.2 kilowatt divided by 545. Mono PERC panels were used. Havells inverter, you must have seen in the diagram. Cost was around 1.67 lakhs and payback period is 6 to 7 years. Payback period means cost by yearly savings. Now the generated power is utilized and excess power is given to the grid. And the net energy is used for billing. So we are getting zero bill for the past few months. For 8 months back, we have installed. So that's what I've written. Beneficiary has to pay for the net energy used. Now another installation is at our institute. There are 2 installations. One is 100 kilowatt solar rooftop. They are using polycrystalline panels and SMA inverter, transformerless inverters. 36 watt, 315 watt peak photovoltaic panels. There are 318 numbers and 25 kilowatt inverters are used. This is the area and 4 to 5 units are generated on a sunny day. On holidays, we pump back energy to the grid. Another on-grid system at our institute on a different building. Rooftop area is 360 square feet and this is the system. So there is a short quiz before the last slide, 2 slides. I will just put it in the chat box. I hope I can see the chat box. Did you get the quiz question?
Yes, ma'am. We are watching.
Yeah, please.
All of you are requested to participate the quiz question that's given by speaker, please.
Yes, I am notifying it again. If any question arises in your mind, please feel free to drop it in the comments or note down.
Once it is done, let me know.
Yes, we can see it, ma'am.
Yeah. So I'll just discuss the answers. The first question, this is a short quiz. First question was choose the one which is not true for distributed generation by renewable sources. So the first 2 were right. Less environmental impact generation at the point of consumption. Those 2 were right. So which is not true is increase in transmission losses because we are consuming at the generation point itself. Now, which of the grid interface system given below has DC to DC converter and inverter? Answer is 2-stage system. Next was choose the most appropriate method for grid synchronization. That was phase lock loop. Other methods, zero crossing detection is there, fast Fourier transform is there. There are drawbacks for all this, zero crossing detection and all. If harmonics are there, there are issues. Next was how many 550 watt peak PV modules are needed to install 2.2 kW on-grid system. That is 2200 divided by 550. Number of PV modules was 4. Then small phase angle difference between grid voltage and inverter voltage for dash transfer to grid. That was active power transfer. I hope you all could do it. Anybody got full 5 out of 5?
Ma'am, 4.
You got?
Ma'am, no, ma'am. I was not able to answer the number 4. That was-
Okay. 2200 divided by the voltage rating of the panel. Total power installation is 2200 and PV rating is 550. So 2200 divided by 550. That is the
Yes,
number
ma'am,
of
yes, ma'am.
panels. Yeah. Okay. So this is my last slide. Some of the research trends in grid-tied PV systems. New materials for solar cells. There are perovskites, graphene perovskites, and different types of solar panels coming to picture. Bifacial, so many types are there. Then usage of wide bandgap devices in power electronic conversion. If you are using wide bandgap devices, you can go for high frequency, high voltage, high current. And if you are going for high frequency, the size you can reduce. So it will be more compact. Size, weight, everything will reduce. The new power electronic converter configurations for better output quality, high power density, high efficiency. Then we need to address the issues due to high penetration of grid PV systems because it is going on increasing around in installation of this PV is going on increasing. And there's a target for 2030 also. So it is going on increasing. Everybody is installing grid PV systems. So we need to address the issues due to high penetration of grid PV systems. Since it is intermittent, it is affecting the stability of the grid. So that's what I've written, grid stability, power quality issues. Then there is a need for cost-effective energy storage systems as well. So that's all from my side. Thank you. If you have any doubts, you may please ask.
Thank you so much, Dr. Mini Rajiv, for your insightful presentation. We truly appreciate the knowledge and expertise you have shared with us today. Now, we would like to open the floor for any questions or discussions, as you said. If anyone has a question, please feel free to raise your hand or type it in the chat. We will address them one by one. So, Dr. Rajiv, if you are ready, we can begin the Q&A session.
Yes. I am ready. Yeah. Kasi Nasir raised hand. Tell me, ask. You can ask.
Okay. Ma'am, my question was page number 18. That was related to control aspect. As you mentioned about that, you have used for DC side control. Here is a method, maximum power point tracking method, and you also mentioned about the particle sum optimization method. Ma'am, is it possible to track or find out the exact location, like using MILP or other optimization problem like particle sum already mentioned about? I said that mixed integer point or others kinds of optimization we can use for tracking the point.
You can. There are papers for that also. People have used, there are many maximum power point algorithm techniques. There are many, and you can use all these techniques. And as I said, this perturb and observe is the, I should say that number of steps in the program is least in that. But incremental conductance and all, it will be higher. So efficiency also will be higher. I mean, tracking efficiency also will be better.
Yeah, ma'am, I have seen some paper about related to that. Ma'am, my second question was grid synchronization. You mentioned about the phase lock loop method. Ma'am, is it also applicable for multiple phase, like 3-phase or something like that?
3-phase also it is applicable PLL. In fact, for 3-phase it is easy to do because you can use this. You can convert that ABC signals to alpha beta DQ frame, that rotating frame, stationary reference frame easily with 3-phase. It is difficult with single phase because you don't have that phase shift in single phase.
Oh, okay, ma'am.
Yeah.
If you don't mind, ma'am, can I ask another question?
Yes, yes.
Okay, ma'am, you have show the residential application, the PV array, and there after that it was array DC disconnected. When
Yeah, yeah.
what is the function of this portion, like array DC disconnected? I didn't get it.
Yeah. This is for protection only. In case of any issue on the AC side, you can disconnect the PV array. Similarly, if any problem is there on the DC side, you can disconnect the residential load using this AC breaker panel. AC breaker panel and array DC disconnect is for protection. One is for the DC side, one is for the AC side.
Okay, so is it work as a switch gear?
Yes, switch gear. Yes.
Okay, thank you, ma'am.
You can see that it is here. These are the ones. This is DC and this is AC side.
Okay, thank you, ma'am.
Yeah, thank you.
Ma'am, I also have a question.
Yeah.
How do transformerless inverters handle grid disturbance or fault?
Grid disturbance, you are telling?
Yes.
Grid disturbance, right?
Yes.
Yes. So one example I will tell you. Suppose there is a sag in the grid. Sag can happen due to, suppose suddenly some machine, big machine turned on. There can be a high current which created a voltage drop, and then there can be a sag, voltage sag, due to some reasons that any reason. I'm not talking about the reasons and all. But if there is a voltage sag, the control algorithm we can change, sensing the voltage sag. You can change the control algorithm to inject reactive power to the grid. So PV inverters, it not necessarily transformerless. Any PV inverter, you can use it for supplying reactive power to the grid in case of emergency. Emergency in the sense for voltage sag.
Okay. So I also have another question that we know the lack of a transformer can affect the voltage regulation or the power quality in the grid connection. So how you will explain it?
What is that? Voltage regulation.
Yeah, the lack of a transformer can affect in voltage regulation and also the power quality in the grid connection.
Lack of transformer and power quality, you are telling.
Yes.
Lack of transformer will not affect power quality. Power quality means the current, the shape of the current, all those things, right? Power factor, then the harmonic content, all that. So transformer, if you are removing, that will not affect the power quality as such.
No, ma'am. I said that power quality in the grid connection.
Okay. In the grid connection. Okay.
Yes.
You are relating it to transformer, no?
Yeah.
So transformer, the only problem is if transformer is not there, if your inverter output is having DC, then it can be transported to the grid or it can be fed to the grid. Otherwise, power factor and all you can control using the control strategy. Okay. And DC, how it will come if the inverter output, whether it is transformerless inverter or other inverters, if the DC output is not, or the average value of the inverter output is not 0. That means there is a DC component in that. So that will get fed into the grid. Whereas if transformer is there, that will not happen. Because if DC is there, transformer will not induce EMF, right? So that advantage is there. As far as power factor and distortion is considered, without transformer, it will not get affected because transformer is not there. Because THD and power factor, all that you can control using the control strategy.
Okay, ma'am. Ma'am, I would like to ask you another question, which is not related to that question and answer field, but I would eager to ask you that question: how you get interested on that topic, just like solar energy or power grid so much. I saw that you got 5 prestigious awards, which means a lot to a person who works on it. So how you get the energy to work on the field?
Yeah. Actually, I started working in this area for my PhD. So once I started working in this area, my guide has given some list of topics to me when I went for PhD. And one topic was this solar PV grid connected system, transformerless system. So all the 3 topics I searched more information about that. And then I found that this transformerless inverter system, when I did PhD, that was some 10 years back story I'm telling, because I started my PhD in 2013. So
Okay.
that time the work done in this transformerless area was little lesser. So I thought I can contribute something to this field, and I started. So once I started working, there are so many dimensions for this. So I got interested, and then I did harmonic compensation also I did. Then this low voltage right through capability also I did. All that I had done. So that POSOCO award and all, based on all this work only I got. And 3 publication in IEEE transaction also based on that work. I hope I have answered your question.
Good evening, Mini ma'am.
Yeah,
I'd
yeah.
like to ask you a question about the load you have used in all kind of inverters. We have seen that you use only the inductive load in all kind of inverters.
Yeah.
Any specific reason behind it?
It is not
Why don't we
inductive. Yes, tell me. Complete, you complete.
Why don't we use their resistive load or capacitive load?
Actually, no, this is not inductive load actually. This is LC filter it is. When you, the inverter output, as I said before, inverter output will contain different frequency components. But we need only 50 hertz at the output. Correct, no? We need only 50 hertz. So somebody has to filter that. So for that, I used LC filters. In this case, that H5 topology, they have divided that inductor and kept it in forward and reverse path. But you can use single inductor also. But only thing you should make sure that in voltage source inverters, since the output voltage is varying, okay, the output voltage is like this. I will show you once.
Yeah, ma'am. So it do only filtration.
Yeah, that's only filtration.
Yeah,
Output voltage is like this. Okay. So you cannot use a capacitor filter at the output. You have to use an inductive filter. Otherwise, there is a rate of change of voltage at the output. So the current will be very high. So first you have to use in L and then C. CSI, it will be the opposite. So this is basically filtration only, filtering only. Yeah.
I got my answer.
Yeah, yeah. Okay. Thank you.
Okay. So any other questions from the audience?
Hello, ma'am.
Yes.
How can transformer-less PV system improve energy efficiency in distributed generation?
How can? Can you tell the question once again?
Ma'am, how can transformer-less PV system improve energy efficiency in distributed generation?
That is distributed generation. See, when you are in distribution side also, you can generate and you can feed. And this can be one of the sources for distributed generation also. So without transformer, you are generating voltage at the inverter output. You are synchronizing it. You are checking the voltage. You are checking the frequency in single phase case. In 3 phase, you have to check the phase also. And then you are connecting to grid. First, you will do that. You will generate. You will check the voltage. First with a resistive load. That's what I have done. I have connected a resistive load and I check the voltage because the voltage has to match with the grid voltage. And then I will connect it to grid. I have connected through a contactor only. So I will check all this and then I'll close the contactor. It was like that.
Okay, ma'am. Second question is, ma'am, what types of inverters are typically used in transformer?
Transformerless you are asking, no?
Yes, ma'am.
Yeah. So all these are there. You call it as H5, Herrick top. There are many, but most commonly used by the inverter manufacturers, I'm telling. For this H5, they are using Herrick neutral point clamp. All these topologies are used. That will be slightly different from the conventional full bridge topology. That 4 switch one, that slightly different from that. Maybe one additional switch, an additional circuit like that.
You get your answer, Shahriar Hassan Ruman.
Yes, thank you so much, ma'am, for coming.
Yeah, thank you.
Any other questions from the audience?
Yes. Can you hear me?
Yes,
Yeah.
yes, I can hear you.
Thank you so much, ma'am, for your brilliant session. We learned many things. Ma'am, you
Yeah.
mentioned on your slide that generated power is utilized and excessive power is exposed to the grid. Ma'am, do you have any battery storage?
No. For grid, this interface, this system, on-grid system you're asking, no?
Yes, ma'am.
Yeah, no. We don't have storage in this. Whatever is generated, we are using the rest remaining power, we are transporting it to grid or we are feeding it to grid.
Yes, ma'am. But ma'am, actually, when in the rainy day or we are not our generated output, when you are using is the grid connected. But
Yes.
if we are storage systems, then we can use for the future for the next time or for when we are not not total.
I agree.
Yes, ma'am.
Yeah, I understood what you're telling. I agree with you. If I use a battery, I can do that. But the problem is battery needs maintenance and the battery life is not that high. So all this will come into picture. So to avoid that, it is better to use, and in our place and all, the power does not go that frequently also. So for us, no, this is a convenient option. Generate, use it, and excess power, give it to the grid.
Okay. Thank you, ma'am. Can you consider any peer-to-peer connection?
Can you consider any?
Peer-to-peer connection. Actually, I mean when we are gather more energy and we can just left to the our right house or nearby house for their need. Then we can earn some money because when we are supply on the grid, their grid price is too much low. And if we just survive on the outer side's house, we can sell our nearly house and we can just earn more money.
Yeah, you are telling you can generate power and you can sell it to the grid, correct? You using solar panels.
Actually, ma'am, I am not selling in the grid connected. I am just selling on the my surroundings houses when they are need to the grid connect or they are need to use their electricity or something.
Okay, like that you are telling. Maybe you can do that. That I am not able to answer that question. You are telling you will generate and you are sell it to your neighbors.
Yes, ma'am.
Ma'am, can I
I don't know what is your...
answer this question?
Yeah, please.
Ma'am, he's talking about the prosumer, like prosumer, the one who will consume and produce also. If there are extra energy, so he will able to sell it to the grid or to the neighbor, near the neighbor. So, ma'am, you only consider the grid. You didn't show the pair with the neighbor, and that was the question.
I agree. What his idea I understood, but then that depends on the policies of your country, right?
Yes,
So
ma'am.
that
It also depends on the
I,
policy.
that is why I did not comment.
Yes.
Yeah.
Thank you, ma'am.
Yeah.
Okay, so any other questions
Ma'am.
from the audience?
Ma'am, I have a
Ma'am.
question.
Yeah.
Ma'am, for the perspective of transporting to the grid of surplus energy, isn't it expensive for individually for the producer to boost around the kilovolt range or something?
It is not expensive, but then initially you have to pay something and your payback period is around 6 to 7 years. So if you consider that, it is not, I don't think it is expensive, and that maintenance, it is not that much what we need. No, you need to do only the cleaning of the PV panels occasionally.
Yes, ma'am. Ma'am, is it possible for the mass distribution system where lots of rooftops are available in a community?
It is possible. You are telling many houses with rooftop panels.
Yes, ma'am. Here the inverter or connecting topology, it can be formed by the community wholly and they can share the whole process. Is it possible?
Yes, accordingly your inverter rating will be, you have to keep. You can do that.
Yes, ma'am.
All ratings will depend upon your what requirement, no, output power. Suppose 2 houses are using, accordingly the power will change. Inverter number of panels will change, inverter rating will change.
Yes, ma'am, I got the point.
Yeah.
Thank you, ma'am.
Yeah, thank you.
Okay. So let's end this question and answer session. I would like to share my screen. Can everybody see it?
Yeah, we can.
Okay. So thank you so much, Dr. Mini Rajiv, for your insightful presentation. We truly appreciate the knowledge and expertise you have shared with us today. Now,
Thank you. Thank you.
yeah.
I'm happy that so many questions came.
Yes, ma'am. Ma'am, I would also say that it's not surprised that you have been recognized with 5 prestigious awards such as ISGF Innovation Award, A.K. Shankar Meritorious Paper Award. We are deeply grateful for your time and for sharing your knowledge with us today. Now, I would like to, it's my honor to call upon the Counselor of IEEE BSMRSTU Student Branch, Dr. ATM Saiful Islam, to share a few words with us. Sir, we are eager to hear from you.
Thank you, Ms. Krishti. And at the same time, thank you so much to the Professor Dr. Mini Rajiv for your nice presentation. Though my work field is a little bit different from you. I mean, my working field is, what is the end of my working field is the start of your field. That means I'm working on the how to improve the solar cell performances and to minimize the different challenges in the solar cells. And after that, maybe this sort of work is needed. How could we feed those advanced solar cells to the grid to generate the power and feed back to the main grid? So I truly appreciate your presentation and also for your valuable time. And already Ms. Brishti mentioned that you got different prizes for your excellent works. So I hope looking forward to hear from you in future. And also, if
Sir,
possible, maybe we can.
Sorry to interrupt. Sorry to interrupt,
Yes.
sir. I am Azmi. I am from IEEE Prime University Student. Thank you, sir.
Okay, thank you. Okay. Thank you. And as I said, also in your work, maybe I'm not that much familiar with this sort of work, but from your presentation, so far I was thinking to improve the transformer-less inverter to convert the DC to the AC and to feed to the grid. Maybe, however, you think about the multi-level inverter to improve the, to adjust the voltage and also the phase to the grid, and all in together with that, maybe the artificial intelligence also can use to address those issues.
Yes.
Okay, thank you. And as I said, maybe in near future we can discuss together to start work. Thank you.
Thank you. Thank you so much. Even AI can be used in the controller part or in the prediction of the PV parts. AI can be used in many places for optimization and all, and prediction, failure detection, all that AI can be used. Thank you so much. Thank you for giving me an opportunity.
Thank you. Thank you, sir, for giving your speech. Now, it's now my pleasure to invite Qazi Nazir Hussain Ridoy, the chair of IEEE BSMRSTU Student Branch, who has been instrumental in making this event a success. Mr. Nazir, we are grateful for your collaboration and support. Please ahead.
Thank you, Azmi. Thank you, ma'am. Actually, it was really a great conversation with you. Especially, I enjoy it a lot because we are looking for such kinds of seminar or webinar where we'll find some knowledge about our field. So it was interesting. Especially, I'm just going to start my thesis. Here is my supervisor is already talk with you, Dr. ATM Saiful Islam. So I think it will also help in my research because I'm just going to start my research on microgrid. So here I can able to use this kinds of inverter so that it can also make a value in my thesis. And thank you so much, ma'am. I think we will meet another session soon. It is as possible if you are free. So thank you everyone, and thank you to Prime University for this kinds of collaboration. I hope we are looking for another collaboration as soon as possible, and especially thank you to Najmul Islam, who is the counselor of IEEE Prime University, and he is also have a great great or something like that who arranged this seminar. He talked with you. Thank you, Miss, and thank you everyone who joined from Prime University and from our bench. Thank you, ma'am.
Okay, then. Thank you. Can I leave?
Thank you so much.
Yeah.
I would like to call our respected associate professor, MD Mustaq Ahmed, a faculty member of Tripoli, a Prime University, and a committed IEEE member, to share his insights and inspire our audience with a short speech. Sir.
Thank you, Masbi. I pay my thanks and gratitude to our honorable keynote speaker, Dr. Mini Rajvi,
Thank you.
Associate Professor at Agnel Charities, for presenting nice presentation, Transformer-less Photovoltaic Grid Interface for Distribution Generation. Also, thanks to respected Chairman, Department of Tripoli, Dr. ATM Saiful Islam, Bangabandhu Sheikh Mujibur Rahman University, and all IEEE member of this session. I especially thanks to our respected keynote speaker for nice presentation. She tried to show out from generation to distribution, initial part to final part, AC load, DC load, and how to reduce the transformer losses if we exempt transformer for distribution system. And the students who are interested to doing research upon these topics, because recent time it is a hot topics worldwide. A lot of research is going on upon these topics. Ma'am will help all the students and teachers who are interested to doing this. I don't want to prolong my speech. Already 1.5 hours is passed. So now I am concluding this session. Thank you, everybody. Thank you.
Thank you all for joining today's webinar hosted by IEEE Prime University Student Branch and the IEEE BS MRSTU Student Branch. We're truly grateful to our esteemed speaker. Thank you so much. We hope you find this session informative and inspiring. With that, we conclude the webinar. Stay safe, stay inspired, and have a wonderful day ahead. Thank you so much, everyone.
Thank you. Thank you so much.